To run a completely offline, real-time speech-to-text system on a standard laptop, you must pack massive computing power into a very tight space. When you are used to relying on cloud APIs, the task seems simple. Developers often expect that building a local pipeline is just a matter of stringing together a few scripts and watching the text roll in. But stripping away the cloud reveals a different reality. Running heavy AI models on a basic CPU magnifies every underlying system error, memory leak, and dependency conflict. Achieving a working local deployment depends on your ability to navigate these hardcore debugging challenges. The first major constraint is the model itself. Standard Whisper models create extreme inference latency on a basic CPU, causing the process to stall. Solving this requires a foundational architectural shift. You need an optimized backend, like Faster Whisper, which is designed to maintain accuracy while drastically reducing the heavy load on the processor. We achieve this efficiency using dynamic int8 quantization. By converting the model from 32-bit floats to 8-bit integers, we reduce volume by 57%, preventing memory exhaustion and allowing real-time processing speeds. For an underpowered machine, aggressive quantization allows these local AI tasks to complete without stalling. Even with an efficient model, you may encounter an exit crash. The program appears to run perfectly, but a system warning reports that Python quit unexpectedly the moment you try to close it. This happens because the application uses multiprocessing to keep the audio stream smooth. When exiting, the main process fails to shut down background child processes, causing a resource conflict. The root of these orphaned processes is often environment pollution affecting your system's path variables. This hierarchical stack shows the conflict. An auto-starting global Conda environment layers itself directly underneath your project's virtual environment. When loading C++ audio libraries, it mistakenly pulls outdated versions from the Conda base. You fix this by disabling Conda's auto-start behavior and strictly isolating the project's virtual environment. Resolving these crashes requires path isolation rather than changes to the application code. The most deceptive error is the silent failure. You speak into the microphone, but the system produces no text and provides no error warnings. Diagnosis begins with the logs. An RMS peak value ARMA 13,000 proves the microphone is active and successfully capturing audio data. If we track that signal to the voice activity detection module, we often find a complete lack of a voice start trigger, failing to identify the speech. These data lines show the breakdown. While volume is high, the Silero VAD probability is 0.069, well below the 0.8 baseline expected for speech. Avoid the reflex to simply lower the passing threshold to force a result. The issue is often a tensor computation overflow in the if-less variant of the model. On certain hardware, this causes the output logic to collapse into a near-zero flatline. Solve this by changing the model's loading parameters or restricting it to a single-threaded operation. Fixes for silent failures come from analyzing these low-level outputs, not from adjusting surface-level thresholds. Reinstalling the OS or guessing at code changes rarely solves these pipeline failures. Sustainable troubleshooting requires a diagnostic loop. Gather log evidence, isolate the root cause, and apply a targeted systemic adjustment. A disciplined, evidence-first mindset is the absolute only reliable way to properly handle the compounding errors caused by strict hardware constraints. With these steps, you can maintain a stable, crash-free transcription system that operates within the limits of local hardware. This stability comes from combining aggressive quantization, isolated virtual environments, and evidence-based log analysis. Success in local AI deployment is found in your ability to systematically navigate these edge cases. Now look at your own terminal logs and apply this diagnostic mindset to the failures you find there.